Okay, so last video we talked about adding vectors. Now I want to talk about multiplying vectors. And it turns out there are two different ways to do that. The one we're going to focus on right now is called the dot product, which is sometimes also called the scalar product. And it's called a scalar product because this is a way of multiplying two vectors where the result is a scalar. It's not a vector. So if you take the dot product, and so dot product, if you were to take that, you'd write that A dot, you put a big fat dot there, B. And this gives a scalar. It gives something that's not a vector. The second, which does give you a vector, is called the cross product. I'm going to introduce the cross product, but we're not going to discuss that till later. This is sometimes called the vector product because it does return a vector. So you would write that A, if you had vector A, you'd write it with a cross like that, A cross B. And this does give you a vector. I'm going to introduce this, but we're going to do more on this later. It's a little bit complicated, and I think it'll just be better if I introduce it when we're actually using it, which isn't going to be for a while yet. So dot product, we'll start with that, and we're going to do this in a little bit of detail. So the dot product, actually I'll start with the definition. So let's go ahead and say dot product. And the definition of the dot product is to say that A, if I were to take A dot B, that's the same thing as taking vector A, and I'm not going to put an arrow above this because this is the magnitude of A, it's not A itself, it's just the number, times the component of B, which is parallel, that means parallel to A. So I'm taking A and I'm multiplying it by the component of B parallel to A, just that component. So what do I mean? Well, let's say I've got vector A, so here's A. That's not a very straight line, a little bit better. Here's A, and maybe, I don't know, there's B. Well, if you look at it, there's going to be a component of B that is parallel to A and a component of B that's perpendicular to A. So maybe if I draw a line here, you might be able to see like this here. This would be the component of B that's perpendicular to A. That's B perpendicular. And this right here would be, this is B parallel to A. So if I took these two components, right, there's a right angle here. If I combine B parallel and B perpendicular, I get B. So these are the components of B. Well, when I'm interested in the dot product, all I'm interested in is B parallel. So this vector right here, B parallel, that is what I'm going to multiply A by when I'm doing the dot product. Just to preview things to come, this is going to be involved later in the cross product. B perpendicular is what we're interested in the cross product. So, well, how would I do that? Well, let's imagine I know this angle right here. What if I knew this angle? I'll use purple for this. What if I knew this angle right here? This angle, I'm going to call this, your book calls this phi. So I'm going to call that phi as well. Well, if you knew this angle phi, you could determine the component of B that's perpendicular by using the cosine. You could say that B perpendicular is B cosine of that angle phi. And so another way of writing A dot B, and the way that we're usually going to write it, is you take A, you multiply it by B, and then you multiply it by the cosine of the angle phi between A and B. And this is typically the way we write A dot B. A dot B is equal to AB cosine theta. Maybe one little quick note of a little note on this angle phi. This could be phi or it could be 360 degrees minus phi. Either one, the cosine will give you the same exact answer. These are identical angles as far as the cosine is concerned. So sometimes you'll see it as phi, some angle phi, and sometimes you'll see it as 360 minus that angle. It doesn't matter which one it is, but just bear in mind there are two angles here that could work. Before we get to the cross product, I want to point out that we could have done this whole same exercise in unit vector notation. So what about if I want to do this in unit vector notation? So in unit vector notation, well, it turns out it's extremely easy to do the dot product if you've got the two vectors in unit vector notation. So a dot b in unit vector notation, a dot b in unit vector notation is really simple. You take the x component of a times the x component of b, and you add whatever that is. You multiply the two x components together, and you add the y component of a times the y component of b, and then add the z component of a times the z component of b. Very simple, very straightforward way of determining the magnitude of the dot product when you're in unit vector notation. And of course this kind of makes sense. You're taking the parallel components and multiplying them together, which is the definition of the dot product. Before I get into the cross product, let's take, maybe this might be, all of this might be clearer if we tried an actual problem. So what if, let's try a problem. I'm going to say, what if I asked you to, what's the angle phi between vector a and b if a is equal to, let's say, 2i plus 3j, so that's vector a, and so the angle between that vector and vector b, and I'm going to say vector b is 3i minus 5j. And I want you to determine for me what is the angle between these two vectors. Okay, so maybe it would be helpful to go ahead and draw these two. These, by the way, these are two-dimensional vectors, not even three-dimensional. We could have k values in here, and it would just be a little bit more math, but wouldn't be super hard. So just to kind of visualize this, here's the y-axis, here's the x-axis, y and x. So vector a looks like something like this, so maybe like that, that's a. And b is going to be, I don't know, something like that. And so I want to know this angle. I'm trying to figure out what is that angle phi between a and b. So let's think about it. Well, first of all, it might be helpful to, since I've got unit vector notation, what is a dot b? Let's go ahead first and just figure out what the value, the actual value of a dot b. What is the dot product a dot b? And it's really easy. I'm going to just refer to this up here. Ax times bx plus ay times by, right? I don't even have to worry about the z's, right? I don't have any z's. There are no k's in here, so there's no z component at all. So this is going to be pretty easy. I'm going to say 2 times 3 is 6 plus, well, what about the y components? What's 3 times negative 5? That's plus negative 15. So it's just 6 plus negative 15 is negative 9. So this is the dot product, negative 9. If all I'd asked for what the dot product is, you'd be done. But I want to know the angle, so to figure out the angle, I'm going to go back up to our original definition, which was a times b times the cosine of the angle phi. And we've got to be a little bit careful because a and b here, this a and b, these are just the magnitudes, right? It's the magnitudes of a and b. And so I'm going to have to actually do a little bit of work to calculate those. So in other words, I'm going to say negative 9, that's my dot product, is equal to the magnitude of a times the magnitude of b times the cosine, times the cosine of phi. So I've got to go ahead and figure out what the magnitude of A is and what the magnitude of B is, and I'm going to use the Pythagorean theorem to do that. Not going to be too hard, I don't think. The magnitude of A, well, that's going to be Pythagorean theorem, the square root of 2 squared plus 3 squared. 2 squared plus 3 squared, and that's going to be like 3.6. Magnitude of B, that's the square root of 3 squared plus negative 5 squared, and that's going to give me 5.8. So now I can go ahead here and put 3.6 in right up there. I can put my 5.8 in for B there, and I'm almost done. So let me just give myself a little bit more room here. So now I'm going to go ahead and rewrite this down here. I say negative 9 equals 3.6 times 5.8 times the cosine of phi. Okay, so what is 3.6 times 5.8? That's 20.9. So now I can say negative 9 equals 20.9 cosine phi. So I'm going to divide both sides and take the arc cosine. So phi is the arc cos of negative 9 divided by 20.9, and that gives me 115 degrees. So in other words, my angle here, this angle here that I've been asked to find, is 115 degrees. So we've now found the angle phi, and that's a good problem because we had to do the dot product using the unit vector notation method to find the negative 9 to begin with, which was, I think, pretty easy. Yay. And then we had to do a little bit of work here to find phi by figuring out the magnitudes of A and B using Pythag, which is mildly annoying, but not too bad. And then we just kind of finished up with a little bit of trig here. All right. I want to just say a little quick word on the cross product, and we'll discuss this in more detail later. So this is now the cross product. So as I'd mentioned earlier, the cross product has to do with, if I want to know what A cross B is, now I'm interested in A times the component of B perpendicular to A. So this is perpendicular to A. So if I were to draw my vectors again, I forget what they looked like, but I think it was something like that was A. Actually, I'm going to make that a little bit bigger. There we go. Okay, I'm going to make this a little bit, I'm going to make my A a little bit bigger. So here's A, and here's B, something like this maybe. Now I'm interested in the component of B that's perpendicular to A. So that's something like, try to draw a perpendicular here. That would be like this, right? This is the component of B that's perpendicular to A, whereas this was the component of B that's parallel to A, right? So this is, now I'm interested in B perpendicular. This is the guy that I want to put in up there. Well, if I know the angle here, this is my angle phi again. If I know phi, how do I find B perpendicular? I'm just going to use the sine. B perpendicular is B sine phi. So, in other words, another way of writing the cross product is to say this is A, B sine phi. And that's all well and good. That doesn't look too hard. And that is, in fact, going to be our definition of A cross B. What I don't want to go into now is what this looks like in unit vector notation. When turns out if you want to do this in unit vector notation and actually figure out what the vector is, the resultant vector of A cross B, it becomes a little tricky. Because what we have here, this is not a vector. This is just, all this is, to be clear, this is just the magnitude of A cross B. This is not the vector itself. To get the vector itself, we need to use unit vector notation, and that's a little bit hairy, I don't want to get into it now. we'll discuss that later when we actually have to use it. All right, so that's all for now.